Hello friends, now we discuss what is the homogeneous linear equation. So an equation of the form x to the power n dny by dxn plus x to the power n minus 1 p1 dn minus 1 y by dxn minus 1 plus p2 s to the power n minus 2 dn minus 2 y dxn minus 2 plus and so on plus pn minus 1 x dy by dx plus pn y is equal to q is called homogeneous 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 linear differential equation where p1 p2 and so on pn are constants and q is a function of x only. Here you can see that an equation of the form s to the power n dny by dxn plus p1 times s to the power n minus 1 dn minus 1 y by dxn minus 1 plus p2 times s to the power n minus 2 dn minus 2 y by dxn minus 2 and so on pn minus 1 times x dy by dx plus pny is equal to q is called homogeneous linear differential equation of nth order where p1 p2 pn are constant and q is a function of x only. These type of differential equation can reduced into linear differential equation with constant coefficients by putting x is equal to e to the power n. You can see that if the given differential equation is homogeneous linear differential equation, then it can be reduced into linear differential equation with constant coefficient when we put x equal to e to the power z. Now you can see here when we put x equal to e to the power z, we differentiate this with respect to z, so we get dx upon dz is equal to e to the power z. Now this can be also written as dz upon dx is equal to 1 upon e to the power z. If we taking reciprocal, so we can see here dz upon dx, this can be written as in place of e to the power z, this we put here x. You know that if the given differential equation is homogeneous linear differential equation of nth order, we can convert this linear equation into linear differential equation with constant coefficient when we put x equal to e to the power z. So x equal to e to the power z, we differentiate this both sides with respect to z, so we get dx upon dz is equal to e to the power z. And we taking reciprocal of this, so we get dz upon dx is equal to 1 upon e to the power z, and e to the power z is equal to x, so in place of e to the power z we put x, so dz upon dx is equal to 1 upon x. Now we are taking dy by dx. So dy by dx can be also written as dy by dz multiplied by dz by dx, and dz by dx you know that dz by dx is 1 upon x here. So in place of dz by dx, we put 1 upon x. So this will be dy by dz times 1 upon x. Now we multiply this x in the left hand side. So we get x times dy by dx is equal to dy upon dz. And if we suppose this d by dz, this is equal to capital D. So this can be written as dy, or we can also written as x dy by dx is equal to d minus 1 plus 1 y, where this capital D, this is equal to d by dz. Now we find the second order derivative of y with respect to x, that is d2y by dx2 in terms of d by dz. Now we find the second order differential equation, second order differential coefficient of y with respect to x, d2y by dx2. So d2y by dx2 can be written as d by dx of dy by dx. And this can be also written as d by dx, and you know that dy by dx, this is equal to 1 upon x times dy by dz. Now we differentiate this and use formula for differentiation of product of two functions. So we suppose 1 upon x is first function and dy by dz is second function. So first we write here 1 upon x first function, then differentiation of dy by dz with respect to x plus second function dy by dz multiplied by, now we differentiate 1 upon x with respect to x. So we find here second order differential coefficient of y with respect to x, that is d2y by dx2. d2y by dx2 can be written as d by dx of dy by dx, and dy by dx, you know that dy by dx is equal to this is 1 upon x times dy by dz. Now we differentiate this with respect to x. So using here formula for differentiation of product of two functions. So we suppose that 1 upon x, this is first function, dy by dz is second function. So first we write first function, that is 1 upon x, then d by dx of second function, that is dy by dz, plus second function dy by dz, then differentiation of first function dy by dx of 1 upon x. Now this differentiation of dy by dz can be written as 1 upon x times d by dz of dy by dz multiplied by dz by dx. Because this is a function of z and we have to differentiate with respect to x, so this can be written as d by dz of dy by dz multiplied by dz by dx plus dy by dz. When we differentiate 1 upon x with respect to x, we get minus 1 upon x square. So this can be also written as, here dy by dz differentiate with respect to z, we get d2y by dz2, and dz upon dx, this is equal to 1 upon x, you know that, and this plus and minus multiplied by minus, we get 1 upon x square times dy by dz, and this is equal to d2y by dx2. Now this 1 upon x multiply, we get 1 upon x square d2y by dz2 minus 1 upon x square dy by dz. Now we taking common 1 upon x square, so this can be written as x square times d2y by dx2 is equal to d2y by dz2 minus dy upon dz. Then this d2y by dz2 can be written as d by dz of dy by dz minus here dy by dz. Now you know that here d by dz, this is equal to capital D. So this can be written as d2y minus dy. That means we are taking common dy here. So we get d minus 1 y. So we can write here x square d2y by dx2 is equal to d minus 1 plus 1 d minus 2 plus 1 y. Here capital D is equal to d by dz and d2 is equal to d2 by dz2. So we generalize this formula. If we take here x to the power n dn y by dx to the power n, we can write this d minus 1 plus 1, d minus 2 plus 1 and so on d minus n plus 1 y. So this is the general formula. If we convert uh, homogeneous linear differential equation into linear differential equation with constant coefficient, so always we put x equal to e to the power z and x to the power n dn y by dxn can be written as this way. If we convert homogeneous linear differential equation into linear differential equation with constant coefficient, always we replace in place of x we replace e to the power z and in place of s to the power n dn y by dxn we replace dn minus 1 plus 1 dn minus 2 plus 1 and so on dn minus plus d minus n plus 1 y. Now we take one example. Now we take this example of homogeneous linear differential equation of second order. You can see here this can be written as x square d2y by dx2 minus 4x times dy by dx plus 6y equal to x. This is the homogeneous linear differential equation of second order. So it can be converted into linear differential equation with constant coefficient. For this we put here x equal to e to the power z and dx upon dz is equal to e to the power z. Always you learn it x dy by dx can be written as dy, where capital D is equal to d by dz. And in place of x square d2y by dx2 you put here d minus 1 y. Now we convert this given differential equation, homogeneous linear differential equation of second order. We put here in place of x square d2y by dx2 we put here d times d minus 1y. In place of x dy by dx we put capital dy plus 6y is equal to, in place of x we put here e to the power z. Now we taking common, this can be written as d square minus d minus 4d plus 6y is equal to e to the power z. So this can be written as d square minus 5d plus 6 times y is equal to e to the power z. You can see that the given homogeneous linear differential equation is reduced into linear differential equation with constant coefficient. This is linear differential equation with constant coefficients. This is second order linear differential equation with constant coefficient. You can see here the given differential equation is second order homogeneous linear differential equation. We can convert this homogeneous linear differential equation into second order linear differential equation with constant coefficient by putting x is equal to e to the power z and in place of x dy by dx we put capital Dy, and in place of x square d2y by dx2 we put d minus 1y, and we convert this equation into linear differential equation with constant coefficient. Now we solve the second order linear differential equation with constant coefficient. This is the d square minus 5d plus 6 y is equal to e to the power z. Now first we find here auxiliary equation. So for auxiliary equation we put here, we replace m in place of d. So we get here m square minus 5m plus 6 equal to 0. Now we factorize this, so we get m square minus 3m minus 2m plus 6 equal to 0. We taking common m here, so we get m minus 3. Taking common 2, we get m minus 3. Taking common m minus 3, we get m minus 2. So the roots of the auxiliary equation are 2 and 3, which are distinct. Now we find the complementary function. So the complementary function can be written as c1 e to the power 2z plus c2 times e to the power 3z. Now you know that this e to the power 2z can be written as e to the power z whole square plus c2 e to the power z whole cube. And you know that for when we reduced homogeneous linear differential equation into linear differential equation with constant coefficient, we replace e to the power z in place of x. So here we write x, so this is c1x square plus c2x cube. So this is the complementary function of the given homogeneous linear differential equation. So this is the complementary function of the homogeneous linear differential equation. Now we find the particular integral of the right hand side. So we write here 1 upon d square minus 5d plus 6 times e to the power z. You know that when we find the particular integral of e to the power ax, you know that when we find the particular integral of e to the power ax, always we replace a in place of d, and fa not equal to 0. It's the formula for finding the particular integral when we replace small a in place of d, and a is the coefficient of x in power of e to the power ax. So here the coefficient of z is 1. When we replace here 1 and 1, we get the particular integral. So 1 square minus 5 multiplied by 1 plus 6 e to the power z. So this becomes 1 minus 5 plus 6 e to the power z. This is 617 minus 5 2 e to the power z. Now this e to the power z can be converted into x, because we replace e to the power z in place of x. Now we find the general solution of the given homogeneous linear differential equation. Now we find the general solution. General solution is y is equal to complementary function plus particular integral, and the complementary function is c1x square plus c2 times x cube plus particular integral is x upon 2. So this is the general solution of given homogeneous linear differential equation. Thank you.